Now, last time tuliongea mambo we mentioned some terms ambazo tunapata katika magnetism na electromagnetism, and we did some calculations. So the last thing we mentioned ni reluctance, na tukafanya hesabu. Now leo tutaingia mambo ya hysteresis. I had given this as part of sijui kama ilikuwa ni assignment ama ni cut. Nikaambia using a diagram you explain the hysteresis loop. Now when I talk about hysteresis ni kama memory. A magnetic material ikiwa exposed to a magnetic field, once that the internal molecules ama the particles within that material zitajialign with that magnetic field, they will be facing in the same direction as the direction the magnetic field is going. Now when you remove that magnetic influence, kama ni permanent magnet ambayo ilikuwa umeileta karibu na that magnetic material, ukiondoa some of those particles ama some of those molecules, and they are known as dipoles, those molecules will some of them will retain that magnetism. Some of them will still be facing in that direction that the magnetic field was facing. Now to demagnetize ama to remove that magnetic influence from a material, we can expose it to external factors kama heat ama force, or we can apply a magnetic field in the opposite direction, so that property of a material to retain its magnetism, once a magnetic material is removed, is what is known as hysteresis. Are we together? Now this phenomenon, your hysteresis, can be explained ama can be shown by plotting the values of let me switch kidogo. Now you can see what mnaweza ona karatasi yangu hapa. Okay. Now we had mentioned some factors ama some terms. We had talked about flux density, and we had talked about, which is usually abbreviated as B, and we had talked about magnetizing force. Magnetizing force, which abbreviation yake ni H. Now when you plot these values, when you have, let's say, the values of B and the values of H, now kisha ukaziplot as a graph, the results is what we call a hysteresis loop. Now what is a hysteresis loop? This is usually the relationship. It can be used to describe the relationship of a magnetic material when exposed to a magnetic field. Now, let's start. When this is point 0. Now, when a magnetic material is exposed to a magnetic field, when we increase the magnetizing force, the magnetism in that material will increase. It will increase linearly, and then it will reach at a point where even as we increase the magnetizing force, the magnetism in that material will not increase. Now this point, let's label this point A. This point is known as saturation point. Saturation point. Saturation point is a point where hata ukiendelea ku increase the magnetizing force, the magnetic field, or the magnetism in that magnetic material will not increase. Sawa sawa. Now, when we reduce the magnetizing force, the magnetism in that material will reduce. Itapungua. Sawa, itapungua. The flux density will also decrease. Now, I want you to note that the magnetism of that material has not reduced to zero. This is the point zero, mahali ambapo that magnetic material had no magnetism. So that material haitarudi zero. So this is what we are calling hysteresis, that a material, once exposed to a magnetic field, it increase in magnetism. But once you withdraw that magnetic field, the magnetism, it will reduce, but it will not go to zero. Some of the molecular magnets, dipoles, will still retain the magnetism. Now, as we continue reducing the magnetizing force further, itafika mahali that that material will lose the magnetism entirely. Itakuwa zero. Now, this point is known as, this is known as coercivity. That you're forcing the magnetic material to lose all its magnetism. And that force that is needed to reduce the magnetism of a magnetic material to zero is known as coercive force. It is known as coercive force. And this is this magnetizing force here. From this point to this point is what is known as coercive force. It is a force that is required to reduce the magnetism of a material to zero. Now, when we change the direction of the magnetic field, si kumaanisha ati the material will not gain magnetism. No, it will gain magnetism, but in the opposite direction. So the magnetism of that material will increase. It will increase, but now in the opposite direction, and it will reach a point where, let's label this D, let's label this C. It will reach a point where that material will reach saturation, but it will be in the opposite direction. The saturation will be in the opposite direction. No matter how much you increase the magnetizing force, itafika mahali in a magnetic material, the magnetism will not increase. So, now when we reduce the magnetizing force, the magnetism in that material will reduce. The magnetic magnetization in that material will reduce, but it will not be at zero. Haitarudi zero. No. Why? Hysteresis. That material has memory. Some of those internal molecules will retain that magnetism, even if we withdraw the magnetizing force, the magnetic field. Now, a force will be required to reduce that magnetism to zero in that magnetic material, that ferromagnetic material. And that is what we are calling coercive force. Sawa. Now, at this point zero, you can increase now you can continue increasing the magnetizing force, and the magnetism will increase, and it will continue until it reaches a point where itafika saturation. Now, this is what is known as a hysteresis loop. It is used to describe the phenomenon of hysteresis. Sawa. This I'd given in your cut or assignment, and I'm nashanga mbona watu hawafanyi, but a few of you have submitted, but not all of you. Now, this is what is known as hysteresis loop. It describes the behavior of a magnetic material when exposed to a magnetic field. This point is the initial point of magnetism in the material. It is zero. When you increase it, it increases linearly. I've indicated this using the dotted line. Kisha itafika mahali ambapo the magnetism will not increase, and this point is known as saturation. As much as you increase the magnetizing force H, the magnetism in that material will not increase. Once you reduce the magnetizing force, the magnetism in the material itapungua. But hata ikipungua, haitafika zero. Reason being is that some magnetism has been retained in that material. And a force will be required to completely reduce the magnetism of that material to zero. And we have said that this force is known as coercive force. Now, when you expose the material, when you expose that material to magnetism, but in the opposite direction, the magnetism will increase, but in the opposite direction, and it will get to a point where that magnetism will itafika kikomo. No matter how much force you increase, that magnetism haitapita, and we will see that that material has reached magnetic saturation. When we reduce the magnetic field, when we reduce the magnetizing force, that the magnetism in that material itapungua, but it will not go to zero. Why? Hysteresis. Hysteresis. That material has still retained some magnetism in the molecules or in the dipoles. When we increase, now there's a force that will be required to reduce that magnetism to zero. Are we together? Are we together? Now these points ambazo hapa kama hii B na hii ni, let's say label it E, F. These points B and this is B and E are known as points of retentivity. These are the points that the magnetism is being retained in that magnetic material. Now what I've just drawn, what I've just described is the hysteresis loop. Sawa sawa? Are you together? Is there any question up to that point? Kuna swali?
Said which points are retentivity? Point A and what?
Upper, point B and point E. The places where once you reduce the magnetic field, the magnetizing force, the magnetism of that material does not reduce to zero. It reduces to a certain figure, a certain value, but it is not zero. That means that that material has retained some magnetism in it. So we call those points of retentivity. Sawa? Okay. Now, this is what is called a hysteresis loop. When you're asked in the exam to draw, to explain the hysteresis loop using a diagram, ni hapa. You can go read more about it so that you can come up with a conclusive explanation, but this is the diagram. Now, hysteresis loss. Let us talk about hysteresis loss. Now, hysteresis loss is a phenomenon where when I increase this magnetizing, the magnetizing force, the magnetism in my material will increase. India. When I reduce it, the magnetization in that material will also reduce. Now, since this, let's say, this is my material. I've exposed it to a magnetic field, and the magnetic field is going in this direction, from north to south. So you'll find that the particles, the dipoles in my molecule will not be aligned in that direction. Now, when I change when I change the direction of my magnetic field, you'll find that these particles, these molecular magnets, easy dipoles, we resist the change. We resist the change of this. Will resist the change of the magnetic field, and this the resistance will be in form of heat. Heat will be produced because it is you have changed the direction. Are you together? Hysteresis loss basically is the losses that are formed due to the change of direction of the magnetic field. The internal particles, the internal molecules of a material will resist, and this will be itakuwa in form of heat. Heat will be produced. So when you have a magnetic material, you have to find one that has low hysteresis loss. We do not want to have excess energy being wasted. We do not want extra heat being produced. Sawa sawa. Sawa sawa. Question. 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 I'm assuming there's no question. So let us continue. Now let us talk about types of magnetic materials. Now, magnetic materials can be classified under three major categories. We have diamagnetic materials, we have paramagnetic materials, and we have electromagnets. Now, diamagnetic materials are materials that, when exposed to an electromagnetic field, they will become magnetized. But now what happens is the magnetism within that material will produce a field that will oppose the external field being exposed to it. Utapata kwamba a magnetic field itakuwa induced in that material, but that field ambayo inakuwa induced in that material will oppose the external field. So you'll find that these materials repel. Are we together? Utakuwa na an external field which is being exposed to a material, a magnetic material. This external field will induce magnetism in that material. That material becomes magnetized. But that field that is induced tends to oppose. The dipoles are going to be arranged in the opposite direction to the external field, so in oppose. Now these materials are weak magnets. What do I mean? When I remove that magnetic field, the external magnetic field, the magnetism in that material disappears. Now such materials become gold, mercury, and the like. Paramagnetic materials. These materials are the opposite of diamagnetic materials. What happens is the dipoles, the molecules within that material, when exposed to an external field, an external magnetic field, and those dipoles will align in the same direction as the magnetic field. So what happens is these materials are attracted to the magnet. Because the field, the magnetization within that material, itakuwa in the same direction as the external field applied to it. But these materials are also weak magnets. Once you remove that magnetizing force, once you remove that field, the external field, the magnetization of that material inaisha. And mfano of materials ambazo can be categorized as paramagnetic materials in sodium and platinum. Ferromagnetic materials, permanent magnets. These are the magnets that we use sana in our day-to-day activities. Now what happens is those dipoles, the dipoles in ferromagnetic materials usually are random, and they have their own magnetic properties. But these magnetic properties usually tend to cancel each other, so they do not show any magnetic behavior. Random, normal. Now, when these materials are exposed to a magnetic field, these molecules usually align themselves with regard to the external field. They align themselves with regard to the external field, and they align. They're in the same direction as the magnetic field. Now, once you remove that magnetic field, these materials do not lose their magnetism. It's not kama zile as paramagnetic and diamagnetic. These are strong magnetic materials. They exhibit the strongest magnetic properties. When you remove that external field, they will retain the magnetism. Mfano ni iron. Iron is a ferrous metal. Cobalt. We use this in the formation of permanent magnets. Now, this is a table that I have drawn that shows the different types of magnetic materials. Diamagnetic, kuna gold, water, mercury. Paramagnetic, we have sodium, platinum, and nickel. Ferromagnetic, iron, cobalt, neodymium. These are just examples of those types of materials. Don't worry, I will send these notes so that you can see them properly. At kama uzioni sahi. Now, those were types of magnetic materials. But now types of magnets, we have permanent magnets, we have temporary magnets, and we have electromagnets. Now, permanent magnets are those that are made from magnetic materials. I mean, those that are made from ferromagnetic materials. What happens is that once you expose these magnets to a magnetic field, now utoe that magnetic field, they will retain their magnetism. Okay, electromagnets, or they're also known as solenoids. What you have is a coil. A coil is usually wound around a core. Unapata waya imefungwa ama it has been coiled around a core. You pass an electric current through that coil ama through that wire. You'll find that a magnetic field will be generated. Are we together? And the magnetic field, the strength will be determined by the current, the core material, and the number of coils within that electromagnet. I'm sure we've seen this in experiments that as a primary and high school. Tulikuwa tunachukua a nail, we tie a copper wire around a nail and we connect that copper wire to a battery. That becomes an electromagnet. So those are the three types of magnet. We have a permanent magnet, we have a temporary magnet, and we have an electromagnet. Now, magnetic patterns, magnetic fields. We can be able to see. The magnetic field is that area around a magnet, and it cannot be felt, it cannot be heard, it cannot be smelled, but we know it is there. Especially this is a bar magnet, Now, how do we investigate this magnetic field around a magnet? In this kwa mfano ya bar magnet, we can take hii magnet kisha tukaekelea a cardboard on top of that magnet, and then we pour iron filings, small pieces of iron. What happens is that you'll find that those ions will assume this shape. Those ions will assume this shape of that magnetic field. Sawa sawa. Using those iron filings, then we can be able to see the magnetic field patterns. Now, the strength of that magnetic field differs. If I use a magnet that is stronger, if I use the magnets of different strength, you'll find that the stronger magnet, these lines, the magnetic, the flux will be closer. Easy lines they'll be closer to each other as compared to magnets that are that are not as strong. Sawa. Now, the magnetism, the strength of a magnet will always decrease as we move away from the magnet. Utapata that even you can see from these lines, you'll see that these lines zinakuwa karibu na the magnet, the magnetism is closer, but as we move, these lines zinaendelea kuwa kubwa. So that means that the strength of that magnet reduces as we move further from the magnet. Now, the direction of this flux will always be from the North Pole to the South Pole. Sawa. Yes. And it is assumed that these lines of flux zikianzia hapa zitatoka from North Pole and South Pole, and then it is assumed that they will go through the magnet and form a complete loop up to the point where it started. Kama ilianza hapa itaenda izunguke kisha ingie ndani ya magnet and forms a complete loop. Sawa. Now, I'm sure we have come across the laws of attraction and repulsion. Like poles repel and unlike poles attract. Sawa. I'm sure this we have come across it. Ukiweka pole, two magnets, and you bring the south pole of one magnet and the north pole of one magnet, the poles will attract each other. When you bring one magnet and you expose the north pole of that magnet to the north pole of the other magnet, they will repel. And this is the laws of attraction and repulsion of magnetism. Sawa sawa. Now, these flux, these lines of magnetism have properties, and I've listed some below. And the first one is that they form a complete loop. It is assumed that once that flux ikitoka from the north pole, it will go to the south pole, and it will go through that magnet and form a complete loop. The second property is once you distort this flux, these lines of magnetism, they behave as if they are elastic. They will return to their original shape and spacing. Ni kama spring. Ukidistort kidogo inarudi to its original shape and spacing. 3. These lines will radiate ama zitatoka from the north pole to the south pole. Always. 4. These lines do not intersect. Never ever. If you're drawing a pattern, a magnetic pattern, usichore ukaona hii line inakata hii line. These lines do not intersect at all. Hata huku ndani ya magnet, they will never intersect. Sawa sawa. Okay. Now, the fields ambazo tumeona hapo, those are the fields because of hizi fields ambazo tumekuwa tukidiscuss hapa are due to a bar magnet. But now we can have a magnetic field due to an electric current. Now, Now, when a current passes through a conductor, let's say this is a conductor over here. Can you see my screen? Okay. When you have a conductor, Apple, and current is passing through that conductor, we'll have a magnetic field being formed around that conductor. Are we together? You'll see that this magnetic field of a current conductor is different than that magnetic field of that bar magnet. In this bar magnet, it is easy because the field will be the direction of that field will be from north to south. But now in a conductor, we have to find how the direction of the magnetic field. Now, let's assume this is our conductor over here. That is our conductor. And we are looking from it from this direction. And the current is flowing in that direction. What happens is the direction of the magnetic field in that conductor will be clockwise. The direction of the magnetic field will be clockwise. If the current is moving from this end to this end, and we look at it from this point, the direction of the magnetic field will be clockwise. And the opposite. If the current is moving in this other direction, then the direction of the magnetic field will be in the anti-clockwise direction. Now, how do we determine this direction? There are two ways. There is something known as the screw rule and the grip rule. We can use these two to determine the direction of our magnetic field in a conductor. Now, the screw rule states that if I have a screw, and let's assume this is our screw over here. Niko na screw hapo. and it is on the same axis as this other, as our conductor. This screw, if I want it to move in the direction of the current, kama nataka hii screw iende mbele, what will I do? I will turn this screw in the clockwise direction. And this screw, this clockwise direction will be assumed to be the direction of the magnetic field in our conductor. If I put it on this other side, and the current is moving in this direction, and I have this screw facing that direction. If I want this screw to move heavy, I will turn it in the anti-clockwise direction. And this direction is assumed to be the direction of the magnetic field. Are we together? This is usually known as the screw rule. Now, when you are denoting the point where the current is coming from and where the current is going in that conductor, let's say this is our conductor. If you see a diagram kama hii, ukiona mahali ambapo pamechorwa X, this denotes that this is where our current is coming from. Current is coming this point. When you see this dot, this indicates where the current is going to. Sawa sawa. In this case, our current inaenda in that direction. Are you together? Yes. Now, that is screw rule. Now, grip rule, nataka mnione sasa. I don't know if you can see me. Now, let's assume this is my conductor. This is my conductor. Now, this is my mkono, grip rule. Nikushika tunashika. If I take my thumb, and say my current is moving from this point to this point, and I take my thumb and I face it, I point it in the direction that the current is moving, my fingers, will point to the direction of the magnetic field. So if my current is moving from this point to this point and I put my thumb along the same axis, then these fingers will show the direction of the magnetic field. If my current is moving from this point to this point, and I put my thumb in the direction of the current, then when I grip that conductor, then the direction of these fingers will indicate the direction of my magnetic field in that conductor. Are we together? Yes. Sawa sawa. That is how we can find, that is how we can be able to determine the direction of a magnetic field in a conductor. Sawa. This is what I was saying. This is what I was saying. When you're told to represent the convention of representing current in a conductor, X will represent where the current is coming from. And this dot will represent where the current is going to. So this is the magnetic field, the flux, the lines of magnetic field around a conductor. When the current is coming from this point, so the magnetic field will be in a clockwise manner. If the current was coming towards this point, then it will be in the anti-clockwise direction. Any questions? Now, magnetic field of a solenoid. A solenoid is essentially a magnetic, an electromagnet. We can use the same. We can use the same rules, the screw rule and the grip rule, to determine the direction of the magnetic field. You can see that the magnetic field of a solenoid exactly kama ile ya bar magnet. Now, I want you to go find out. This will be a homework. Using the screw rule, the grip rule, how can we find the direction of the magnetic field of a solenoid? When you meet on Friday, I will ask Benjamin, Maina, and Cheryl. Nitawauliza. I want you to explain to me how to determine the direction of the magnetic flux in a solenoid. Sawa. Screw rule and the grip rule. In this case now, the fingers, these are 4 fingers, will be placed along the axis. The axis of, will be in the direction of the current. In the conductor, the direction of the current ilikuwa the thumb, so that our fingers can show us the direction of the magnetic field. But in a solenoid, these fingers will now be in the direction of the current, and then this thumb will now show us the direction of the magnetic field inside the solenoid. So go find out how we find the direction using the screw rule and the grip rule. Sawa. If you're together, please unmute and say I'm present. Naona Maina hajaongea hii class yote, amenyamaza kabisa. Maina, uko na sisi? Okay, it seems that he's not with us, but let's continue. Now let us introduce the phenomenon known as electromagnetic induction. Now, if I was to ask you, how does an alternator work? Alternator ile ya gari inafanya kazi namna gani? Sisi hapa ni automotive engineers. Alternator ya gari inafanya kazi namna gani? Hiyo ni homework nyingine. Find out how an alternator works. But alternator and even the generators, hizi ambazo tunatumia katika manyumba na industries, use the principle of electromagnetic induction to produce current. Now, when you move a conductor, we have a magnetic field. When you move a conductor and it cuts those lines of flux, what happens? We induce a voltage, an electromagnetic force in that conductor. That induced voltage in that conductor produces a current. I want you to note this point. This conductor, that circuit, has to be closed for that current to be produced. I have a magnetic field, and then I have a conductor, a circuit. That magnetic field is usually cut. If I have a magnetic field and then I put a conductor inside that magnetic field, it will cut those lines of flux, and we'll have an induced voltage, an induced EMF in that conductor or in that circuit. Now, if that circuit is closed, it forms a complete loop, then a current is produced by that induced voltage. Are we together? And that is a principle of electromagnetic induction. This was in your assignment or in the cut. I'm not sure which one. This is a principle of electromagnetic induction. Now let me see if I can here. Let me use this to explain what I mean. We have a magnet that produces a magnetic field, and we have a conductor that has been imekwa kama loop. Now, if I put this magnet inside this conductor, we have a measuring instrument known as a galvanometer. It is just a very sensitive type of ammeter that is used to measure deflection. Now, if I put this magnet, ambayo iko na magnetic field, inside this coil, you'll see that these coils will cut those lines of flux, and a deflection is measured. That deflection that is measured indicates that a current has been produced. If I remove that magnet, then the deflection itarudi zero, because there is no coil. Hakuna coil ambayo ina cut those magnetic lines. Now, if I put this magnet, this magnetic field, and if I put it in the coil and it cuts, the coil, the conductors cut that magnetic field, the deflection itakuwa produced in this measuring instrument, indicating that is current. If I pull the magnet, I take the magnet and cut, and I put it, I pull it in the opposite direction, a deflection is also measured, but in the opposite direction. Sawa sawa. Are we together? This is the principle of AC. AC, how AC is produced in a generator. AC current. Now, when I put this magnet inside these conductors, and I don't move it, nisisongeshe, there will be no deflection. Reason being that there is no relative motion between the magnetic field and the conductor. So there is no lines of flux being cut. there has to be relative motion for the current to be produced. There has to be relative motion between the magnetic field and the conductor, so that we can have induced voltage, and that induced voltage in the conductor produces a current if that circuit is complete. In this case, we have a complete circuit. So there is a current which is produced, which is being indicated by the galvanometer. Now, if the speed at which I move this magnet, if I move it at a higher speed, then this deflection will be higher, which indicates that the speed of if I increase the relative speed between the relative motion between the magnetic field and the conductor, then I can be able to increase my current, my induced current. So, if I use a stronger magnet, then the deflection is doubled or tripled, depending on the strength of my magnet. If I increase the number of coils, the increase the number of conductors, then my induced voltage, my induced current also increases. So this is just a very simple experiment which is used to show how the interaction of the movement between a magnetic field and that of a conductor produces a current. Electromagnetic induction, we are producing current. And how are we producing current? The magnetic field and the conductors interact. The movement causes the induction of an EMF in the conductor or in the circuit. And if this circuit is complete, then that voltage, the potential difference produces a current. And that current now here is being measured by a galvanometer. Now, we can have in this case tumekuwa tukiongea about electromagnetic induction by moving the magnet. We can move the magnet within the coils. The conductor is stationary and the magnet is moving. We can also have the principle of electromagnetic induction by having a permanent magnet ambayo imekuwa haisongi. The magnet is not moving, but we have the conductor moving. Sawa. And this is usually katika zile generators, an alternator, a generator. And that's how they operate. We'll have a permanent magnet fixed in place, and we'll have a conductor, coils, rotating within that magnetic field. And these conductors will be cutting. Yes?
So it means that the alternator of a car is different from a generator?
No, it is the same. But what do you mean? What do you understand by a generator?
Like, I'm not really convinced that any of the but that one of alternator of a car normally is that the magnet is the one which is rotating.
Ndio nasema sasa. Kuna tofauti. We can create, we can have the principle of electromagnetic induction by rotating the magnetic field and having the conductor stationary. We can also have electromagnetic induction by rotating the conductor and having the magnetic field stationary. And that is how a generator, especially AC generators, we have DC generators and we have AC generators. AC generators, utakuwa umepata that the alternator is a very good example. And that's what nimekuambia sahi. Uende uangalia how an alternator works. And even an AC generator. You'll find that a very simple form of an AC generator that produces alternating current is the magnets are fixed, ni permanent. And we have a conductor rotating within the magnetic field. Those as the conductor rotates, it cuts those lines of magnetic flux. These are lines of magnetic field, which induces a voltage in that conductor. Now, once that voltage is induced in the conductor, it produces a current. And in this case, it's an AC current. It's alternating. Now, that is the basic principle of electromagnetic induction. Nilikuwa nimeambia mfanye assignments, nimeona kama assignment 2-3 ama cuts 2-3 watu wafanye. Haya. Mkipata 0 msiseme, don't complain. Now, we have laws that govern this electromagnetic induction or magnetic circuits in general. And the first one that we will talk about is Faraday's law of electromagnetic induction. Na inasema namna gani? Now, what we've been talking about. We have an EMF that is being induced in a conductor once that conductor cuts the magnetic field. So that is what we've been saying, and it is known as Faraday's law. Once you have an EMF, once you have a voltage being induced in a conductor, once that the flux changes, the reason why the induced voltage is being formed, is being produced, is because the flux is changing, because you are cutting that magnetic field at different angles. So in a badlika, the flux that is being cut at 0, at 20, at 40, at 60 degrees is different. So once that flux changes, then we have an induced voltage being formed. And the principle that, the law that supports that that property, that phenomenon, is known as Faraday's law of electromagnetic induction. Now the magnitude, how big that voltage is, how small that voltage is, it is proportional to the rate at which that flux is changing. So if you increase the rate at which that flux is changing, then the value of the magnetic, the value of that induced voltage increases, as I was explaining in this diagram. If I increase the speed at which I'm cutting that magnetic, if I increase the speed at which I'm moving this magnet into the coil, then the deflection in my galvanometer will also increase in speed. So kama naeka haraka natoa, then this speed will also increase. Sawa. Sawa. If I double the speed, the speed at which I am putting this magnet, the speed, sijui kama mnaelewa hiyo vile nasema. Unajua watu wamenyamaza tu. Tunaelewana? Ama kuna swali? Now that is what I was talking about. The magnitude, the value, how big, how small that induced voltage will be proportional to the rate at which the magnetic flux is changing. As I was explaining, the rate at which that line, the conductor, is cutting those lines of flux changes. So let's say I have my permanent magnet and I insert a coil and naiweka katika coil. If I kama naiweka na haraka, then the deflection, the magnitude increases, as I've shown in that diagram. Now, if I'm let's say in this diagram, if I'm cutting the magnetic field at a constant speed, then I can have an alternating current being produced. And that is basically the generation of AC current. Kwa sababu unapata ile speed ambayo the conductor is moving within that magnetic field is usually constant. If I have a motor rated, let's say 200 RPM, itakuwa 200 RPM. So you'll find the conductor within the rotor, itakuwa ina cut those magnetic lines at 200 RPM. So you'll find that there will be a constant current being produced. Now, we have another law that governs electromagnetic circuits, na inaitwa Lenz's law. Now, we have induced a voltage in a conductor kwa sababu it has cut the magnetic flux, the lines of magnetism. That induced voltage sets up a current in the conductor. Now, this current that is produced will tend to oppose. Itakuwa ina tend to oppose the change. That flux that is responsible, those lines, that magnetism that is responsible for creating that current, will itakuwa opposed by the current. What do I mean? If I have an induced voltage going in this direction, it will produce a current that will be going in the opposite direction. It is opposing. This is Lenz's law. Lenz's law. It is used inatumika sana sana to show the direction of the induced current, the current being produced. If I have a conductor that is cutting a magnetic field, and the induced voltage in that conductor inaenda in this direction, then we'll have a current that is going in the opposite direction to oppose the flux, to oppose that motion. Are we together? Please note these things down. You might not understand what I'm explaining sahi, but enda mahali ukaandika ukaangalia YouTube video, what is electromagnetic induction, ukaangalia Faraday's laws, ukaangalia Lenz's law. Revise, tusome. Now these laws are the most basic laws when in magnetic circuits. Now an alternative of determining the direction of the induced voltage in the electromagnetic direction, the induced voltage in the Fleming's right hand rule. I don't know if you have come. Sijui kama mnaona hiyo diagram vizuri. Is it clear? Kama ni ndogo sana. Okay. Can you be able to see it now? Mnaweza ona sasa?
Yes.
Now, Lenz's law was being used to determine the direction of the current. Now we can use another law known as Fleming's right-hand rule to also determine the direction of that induced voltage. Now, what you do is you take your right hand and you take your thumb, your first finger and second finger, and place them at right angles to each other. So the first finger and the thumb will be at a right angle to each other, and the first finger and the second finger will be at right angle to each other. Now, when you place this hand and the thumb will indicate the motion of the conductor, the motion in which the direction of motion. If your conductor is cutting the magnetic field in this direction, then this thumb will indicate that. Let me. Now, as I was saying, you have your fingers at right angle to each other. You can do this with me. The thumb will indicate the motion of the direction in which the conductor is cutting the magnetic field. The first finger will indicate the direction of the magnetic field. Now, this finger will now indicate the direction of the induced EMF. If you have the direction of the motion of the conductor and you have the direction of the magnetic field, then this finger, the second finger, will indicate the direction of the induced voltage. Sawa sawa? This is an alternative of determining the direction of the induced voltage. Lenz's law will, tumesema that the current produced will oppose the induced voltage. Ama the flux, the current produced will be in the direction that will oppose the flux causing it. Ama the force causing it. If you're told to find the direction of that, current, ama the induced voltage, you can also use the Fleming's right-hand rule. The thumb indicates the motion, ama the direction of motion in which the conductor is cutting the magnetic field. The first finger will indicate the direction of the magnetic field. The second finger, at a right angle, will indicate the direction of the induced voltage, ama the induced EMF. So, are you together? Now, the diagram that I have shown here is we have a magnetic field. We have a magnet, and we have the magnetic lines, the flux. The conductor is cutting the magnetic lines. Sawa sawa. Now, the value of the induced voltage in that conductor can be found by taking, I want you to write down these formulas. Yeah? Let's write down these formulas. The value of the induced voltage in the conductor will be given by the flux density times the length of that conductor within the field times the velocity at which you're moving that conductor within the field. That will give you the value of your induced voltage. Now, if that conductor is cutting the lines, the flux, the magnetic field at an angle. Say it is cutting the lines. The angle between the magnetic line and the conductor is 90. Sindio? The sijui kama mnaona. Can you be able to see? The conductor in this case is cutting the lines of flux at an angle of 90. The induced voltage, the induced EMF in that conductor will be the magnetic flux density, B, times the length of that conductor, times the voltage, the velocity at which you are moving the conductor within the magnetic field, times the sine of that angle. Now, since in this case the sine of 90 is 1, then we can use this formula upper juu. But if this conductor is cutting this magnetic field at an angle other than 90, 80, 70, 45, 20, then we use this formula. We have to take into account that angle. Are we together? In this case, it is cutting the angle at 90. The flux at 90 degrees. So sine 90 is 1. That's why we can use the first formula when you have a conductor cutting the angle at 90. But if it is cutting the angle at another angle, at a different angle other than 90, then we have to take into consideration that angle. Now let us do this example. You have been given a question and you have been told to that a conductor is 300 millimeters long and it moves through a magnetic field at a uniform speed of 4 meters per second at right angle to a uniform magnetic field of flux density 1.25 Tesla. We had talked about max flux density, so I won't have to do them again. Now you've been told to determine the current in the conductor when A, it is open circuited, means that the circuit is not complete, and B, when the circuit is connected to a 220 ohm resistor. I'll give you a minute to write down that question and then we'll calculate it together. So. Now, I want to switch my screen so that I can show my calculation. We can see. Can we see?
Yes.
Okay. Now, from the formula that we have seen, remember that the value of induced EMF is given by B, which is the magnetic flux density. Magnetic flux density times the length of that conductor times the velocity, sine of the angle at which that conductor is cutting the magnetic field. Sawa. Now, we've been told that the length of the conductor is 300 millimeters. Are we together? And it is moving at a speed of 4 meters per second. The magnetic flux density B is value yake ni 1.25 Tesla. Now, determine the current moving. I mean, when that circuit is open circuited. When I say that it's open circuited, that circuit, I mean, if I was to draw an open circuit, a very simple open circuit is the terminals. This circuit is not complete. Now, remember, when you're doing your calculations, always make sure that you change the units to their base units. In this case, tumepatiwa in millimeters. So when you change the length into meters, utakuwa ni ngapi? 0.3 meters. Now, the value of the induced voltage will therefore be 1.25 times 0.3 times the velocity. The velocity is already in its base unit, meters per second, so times 4. Now, you can either include this or not. If you're being told, kwa sababu swali ishakwambia that the conductor is cut in at a right angle, so sine of 90 is 1. So you can put it, you cannot. But if you decide to put it, then include upper times sine 90. If not, you can just say 1.25 times 0.3 times 4. So it is up to you. Now, what is the value of the induced voltage? 1.5 volts. Are we together? But that is not the question. That is not our question. Tumeulizwa tutafute nini? The current. We are being told to find the current when the circuit is an open. Who is this who is trying to steal? Now, we have been told to find the current. Now remember, when we started this electromagnetic induction, niliwaambia that the phenomenon is that when a conductor cuts through a magnetic field, an EMF is induced. But when that conductor is closed, I mean when that circuit is closed, if you have a closed circuit, then current is formed. Are you together? Now, in the first part of the question, tulikuwa tunaulizwa that we find the current flowing in the conductor when the ends are open circuited, meaning that that circuit is open. It is not a closed circuit. So, even if there is an induced voltage in that circuit, we will not have any current. Current will be 0. Sawa, because that circuit is not closed, so there will be no current flowing. The induced voltage will not be able to produce the current. Are we together? In an open circuit, the current will be 0. In any electromagnetic circuit, if that circuit is closed, then current will be produced. If it is open, we'll have induced voltage, but we'll not have any current. Now, the second part of the question is, yes? Kuna swali? Is there a question? Okay. Now the second part of the question is you find when the end. Now we are being told that the end of that circuit is connected to a resistor. Now our circuit is no longer open, but it is closed. We have a resistor that is 20 ohms. Now how do you find the current? I mean, how do you find the current when you have a voltage, the induced EMF as 1.5 volts, and you have a resistor of 20 ohms? How do you find the current?
0 over R.
Yes. We'll use Ohm's law. So the current will be the voltage, which is 1.5 divided by the resistance. Na itakuwa ngapi? 0.075 amperes. Are we together?
Yes.
Tuko sawa mpaka hapo?
Yes.
Na umepata your 5 marks just like that. Let us look at another example. Let's try this example. You're being told that At what, the question is, at what velocity must a conductor, which is 75 millimeters long, cut a magnetic field of density 0.6 Tesla if an EMF of 9 volts is to be assumed? Now, you're being told to assume that the conductor, the conductor is cutting the field at 90 degrees. It's mutually perpendicular, meaning that the sine of 90 is 1, so you don't have to include that in your calculations. So at what velocity must that conductor cut the magnetic field if you want to have an EMF, an induced voltage of 9 volts? Mimi atatufanyia hiyo, mfanye na mtu atupatie answer ama solution. Have you been able to write the question? Okay. I'm hoping everyone has been able to write the question. Now let us do, fanyeni kisha mnipatie answer and then tuone kama we'll get the same answer. What is the answer that you have gotten? Cheryl, umepata nini? $200 meters per meters.
Will it be millimeters or meters?
Meters, because remember you changed this to meters, isn't it?
Yes, sir.
Yeah. So I'm assuming you are being able to like easy questions here, as long as you have the formula and you can be able to apply the formula, then these questions will be very easy. Sawa.
Yes.
Okay, now let us do we stop from there ama tuendelee?
Can you give us an example which is different angle other than 90?
Now, in these questions, tumekuwa tukiassume that you can do the same question, and then now
Yes.
you're told that the conductor is cutting at 20 degrees. What I want to do right now, I just want to introduce you to the concept, so that when I give you an assignment this week, then you can be able to apply that concept. Unaona?
Yes, yes.
So that nikikupatia swali ambayo iko na angle utapotea. Sawa.
Yes.
Now for now I'll reach there. I don't want us to take a lot of time kwa sababu hata nafaa kwa class nyingine sahi. But on Friday we will continue with this inductance, and then we will find the energy stored in an inductor. And I think hii topic itakuwa imeisha, if I'm not wrong. Yeah. For now I think tutaachia hapo for today. So thank you for coming. Nimeshukuru sana.